read current analysis also, like in the last paper I did mention this. So read current. So read current, how you can mention read current, like see. So this is the circuit. So I told the reading operations. See. So in read operations, this should be on. This TG should be on. On means WL should be rising because this should be falling pulse. So this one should be on, this one should be, because here 0, here 1, so this is on. So parallelly this, if VL is high, so this parallelly will discharge like this. So during the read operations, current passing through this, the current passing through MN or current passing through this plus this, so this current plus this current is equal to this current. So if you are getting the current passing through MN1, that is equal to MP3 plus MN3, that is the read current. So that read current also we can measure. Okay, and write time also, writing time, sir. So this is a write operation case, not read operation. Write operation, see, if here 0, if you are applying here 1, so this will current will flow this and start raising, and if here high, here you are applying 0, so this will start discharging. So parallel path, it will discharge very fast. So this H node start falling and this L node start raising. So when L raised by 90%, that is the time taken to raise 90%, that is called right delay time, or falling 90% that of H node is termed as right delay time. Get it? So that is a okay. So yeah. So read current I got how you can find. So then read current at different supply voltage we got. So for conventional 60, this is a different supply. Zigzag 80, that's the given by us. That's why I added like zigzag or G80. It is in microampere. So you can see the comparative result. Okay. And same you can plot. Okay. So this comparative result you can see which one consuming more current during the read. Okay. So current, both current and load current. So you can say in terms of current. Similarly, another parameter like read access time. The read access time same way. 60 I already got very well. So same way we will calculate for this thing. It is a conventional AT. It is a proposed. So here you can see I told you sometimes you don't need all parameters. It will be good. So here read delay showing. Which one is our? That is purpose. Which is purpose? Black. So read current is more, which is a little bit slow. Get it? But other parameters is good. Okay. So yeah. So write access time C. That is the right. So I want to writing will be very fast. Get it? So see here it is a better. Means low delay. It means the writing time will be less. So writing will be very fast. Okay. Then leakage current. Oh, write power. So during write time, how much power displacement is happening? That power is calculated. So for conventional 60, zigzag 80, and our photos. You see here, this highlighted by blue color, showing write power is less as compared to other. Even in graph it is very clear. The lower graph line, it is showing very less write power in our photos. Get it? So that way you have to compare this write power. Then leakage power. Leakage in previous work I didn't mention very well. Leakage just formula we just see here. Actually, leakage means we are not reading and writing. That means this is off, this is off. So this one off means getting. Sorry. If this one and this one is off, how you can make this off? We have 0, so this is off, this is off. But still power dispersion, still leakage current is happening. So how leakage current? So if you go in MOSFET based leakage component, so see here different component, blue color, red color, getting this this dot. So here it is mentioned. Yes, see this I leakage. So first I subthreshold of conventional 60, junction leakage and gate leakage. Basically, three components we consider: punch through and bend to bend contact leakage is a very minor contribution that one is not considered. So only these three major leakage component and how this then in paper, the writing paper should be very clear. So whatever it is happening internally in the MOSFET or device, that only you have to represent. This is representing here leakage that this is the drain or source like that. So drain, this is leakage, this is gate leakage. Okay, similarly, and this device, this is everywhere leakage happening. So overall, you are not writing reading like in system I am not doing anything, but still power dissipation or memory is there, memory data is stored. That type of power dissipation will happen. So that power we have to calculate, and overall that power should be less. You should design a circuit such that it consumes less power. Then battery backup will be more. Then you can put in your pocket and you can carry it up to 3 days. No issue. Getting it? Okay, so in that way we have to suggest a component mentioned like for this 60. Similarly, this for this leakage current for 7 conventional 8 whatever you are designing, or that one you have to calculate. Here just mention this is for 60. So three component: subthreshold leakage, then this is also for MP2. This is the MN4 subthreshold. So total subthreshold leakage was calculated. Then total gate leakage calculate. Then one more. Junction leakage. Yeah. So this junction leakage here. This is subthreshold leakage, junction leakage. This is the gate leakage. So this on this plus this, that is your total leakage. So I leakage into VDD. I leakage into VDD, that is the leakage power. So leakage power, you can one more line you can write it. So here it is okay. So P leakage is a VDD into I leakage, and I leakage total we got. Okay. Similarly, for 80, same way, like 60. I'm not going to write this. So for this 80, proposed 80, and in that case also like this equation in previous slide, not mentioned. So this P volt or P leakage, VDD into I leakage you can, and finally leakage current you can calculate. So finally, that is the theoretical aspect. Why is the leakage getting? Why loss, power loss? So theoretically as well as practically. So in guidance or in access price, we will calculate, we simulate and to see for conventional leakage power 1.89 at 0.44 volt. Similarly, at the current supply voltage for this conventional zigzag gate and proposed. Again, what we are getting, our proposed one, it's showing lower leakage power as compared to this. Here only I compared two circuits. You can compare 5-6 other circuits. Then it will be good. Getting it? Okay. Sometimes latest. So like if you are designing 80 new, then what you do? Recently 60, 70, 80 if paper published. That paper first and get the performance parameter. Then try to design new and compare. Not like this is conventional. This is a very old and standard. Everyone, all authors, they are mentioning in each paper. That's why I also am here. Okay. So area comparison. So I told that area, like area has to come. So layout. This is for yes, only two layout I plotted here, one conventional 60 and that proposed one. Even conventional 80 also, but in paper we are not putting all layouts because less we want to put one less because if you put more area then large actually in paper large area it takes your layout. So what we do, only one layout put and other calculated results. So see here only one of proposed one. Here it is a I'll explain this layout later. Okay. So see, this conventional its area is 0.518 micrometer. It is 1.0. It is a 0.77. You can think, sir, why we have more. See, this zigzag 80, it is 1.0 micrometer. We are getting 0.7. So as compared to this, our area also less. Sir, how you are getting less area? That's also possible. Because same number of MOSFET, but you are selling less area. How it is possible? In layout, you know, designer what they are doing, cost, floor planning, placement, routing, like अगर आप बहुत बढ़िया इंजीनियर हैं आर्किटेक्ट तो सिविल इंजीनियर हैं या आर्किटेक्ट तो क्या करते हैं लेस एरिया में ही some architect can design very good house, some architect can design not good because they didn't plan properly. Like where we have to put kitchen, where we have to put dining hall, where we have to put balcony, like that. If you are not putting properly, then it will take more area. That's why architect also what they are doing first planning placement. So here in layout also same way proper placement should be there. If you place a different place of MOSFET or PMOS, then its area will be more. Getting? Is it clear? Even between two devices, according to layout design rule, some distance should be mentioned. If you are putting more distance, then area will be more. So that layout engineer based on perfection, you can get less area. Getting? So if you are expert in a layout design, then definitely sometimes why not more number of devices, but area will be less. Okay, so area also less. So area wise our mark is a good like that. Okay, same again. So another parameter, sir, that is very important. Noise margin. I already taught. Noise margin is the maximum noise that can tolerate by your circuit. So during read operations, maximum noise that can tolerate by the read resonance. During write operations, maximum noise that can tolerate, that is called write resonance. During hold, we are not reading a write. That time also is noise coming and tolerating by your circuit. So we are checking maximum noise. If maximum noise tolerating capacity means more stable, more good. Stability very good. So see, static, read static noise margin and write static. So this graph basically for write static, this is the read static. So here it is not a butterfly curve for this T circuit. This is our support work, this is conventional, this is zigzag 80. So what? In graph only you can see larger side length of the lobe, higher RSN. So here this big side, square side, which one have big black color? Black color means zigzag 80. Our proposed one like this. Get it? So in terms of read SNM, during read, our circuit can tolerate less noise. So as compared to RSNM, our circuit is not very good, little weaker. Okay, but see, I told because we are using TG. So TG, WSNM in this case is dot dot. Get it? So WSNM, suppose it is blue color, dot dot. So this larger square, it is very high. So this higher is 150 millivolt. Conventional 80 is 100, it is 50 millivolt. So our WSNM is very high. So during write time, more noise can come by getting. So this is the write noise margin. That is a yes. So this is the equality matrix. This is not mentioned in any paper. First time this parameter I introduced. Okay. Electrical equality matrix. So see, I told RSNM should be high, so you can put in numerator. WSNM also should be high, should be numerator. All these parameters should be less. Okay, it is in denominator. So conventional it is 82, zigzag 38, and our 292. So this representing higher equilibrium is the better circuit. Okay? So this proposed astral cell exhibits 3.5 times higher equilibrium as compared to conventional zigzag technique. Okay, so no doubt this one will be acceptable. Okay, then some reviewers asked up to that first time I get work. Then reviewers they asked highlight of the contribution made by this work. So they mentioned some reference like in paper 189, 180, 179. Okay, you compare with this work also. Reviewers have some doubt. They told compare the result with this. Okay, then again simulation I done this checked. So area of the is
one motion is there. You have to take in the 186.
No, 180 nanometer. No.
186 reference you take here.
Yeah.
This one.
No, actually what is this 186 actually some slide I kept that is the PhD one. So in PhD this is it is sequence wise 186. So that one I didn't take everything. So the paper 186 I am taking. In some review paper is there. Review paper
In the result.
Yeah.
So 15 nanometer.
What?
Technology is 15 nanometer.
16 nanometer.
22 earlier I was using
Right now 16 nanometer. Right now I'm planning below 16, but that library technology node is not even in most of the institute cadence it is a minimum 45, but in access by synopsis tools it is a 16. So I'm using 16. So that part finished. A lot of papers here we published. Just you can see I'm not going to this. That is this other 90 that is also published in 2020, 21, and same way other concept by D.T. Moss. We design other papers. The similar paper not mentioned all here. Yeah, I'm coming this. That is a new device. So 30 minutes. So like memory storage morning time. Memory storage is the fourth missing passive element. Like inductor you know, capacitor you know, and resistor you know. But still most of the engineers and faculties those are not working in that they know only three passive elements. This is the fourth missing element. Fourth passive element. What is that? That is actually two-terminal device. This is also two-terminal, resistor also two-terminal device, capacitor also two-terminal device, inductor also two-terminal device. Get it? So, memory is a two-terminal device which resistance can change by applying potential difference across the terminal. So, what is the difference? Because in inductor also same thing happening. Capacitor, what is that thing? It is the four fundamental element of the resistor, capacitor, and inductor I. According to Chua, what is that? M represents memory step, and M is nothing. This is del I by del Q. You know. Okay. So this is the device. This is the titanium oxide doped. This is titanium oxide undoped. So when you apply here potential, this is doped division will shift. When this W increases, so this W becomes like equal to D. That times the resistance will be very less. Getting a point. So that resistance, more resistive, low resistive, it depends on potential. It's symbol like this. If you draw its voltage transfer characteristics, it looks like a hysteresis curve. Due to this, that is inversion result is there. If you remove a power, even it will store across this device voltage. Getting how it is possible? See. So that is a very interesting. See, this is the four variables. You know the voltage, current, flux. Charge and flux. So this how many possible relations? How many possible combinations? This four variables. So voltage, current, resistance, current, flux, inductance, charge and flux. What is the Getting? So this one is nothing, it is the membrane resistance. So here it is very good. So see, this is the current, charge, flux, voltage. So the relation between voltage and current, that is the V is equal to IR. So R is the resistance, so dV by dt is equal to R resistance. Getting my point? So the relation between voltage and current gives the resistance one. Other relations, voltage and charge, that is the dq is equal to C dV. So C is equal to dq by dV. One more relation like this, charge and current. So dq is equal to I dt. So I is equal to dq by dt. Getting? Similarly, flux and current, d phi is equal to L di. So this L inductance gives the relation or proportional constant between d phi and di. What about this? Other one more, so d phi d dt, that is the voltage and flux. One was missing. What is that? Charge and flux. So that is invented by Alan Chua. So that is nothing. It is a relation between charge and flux. The rate of change of flux per unit charge is nothing, it is the memory state. So d phi is equal to m dq. So this m is nothing, memory state. Getting a point? So that is same way written. So this was missing. Now it is the memory state. Okay. So memory state is an emerging device which actually it is good because if you are using this, then whatever the problem was in a static RAM, that is a volatile issue. That volatile issue you can sort out by using memory step. We can design non-volatile. So power is gone, data will be getting in earlier like in cache memory. If data gone, no, power gone, data gone. Getting a point. But if you are designing as RAM by using a memory step, then if the power gone, still data will be there. Getting? Actually, this is designed, invented systematically in 1971. Leon Chua discovered the fourth fundamental passive element, that is called memory step, while trying to establish the basic relationship between charge and flux. That time they discovered. But the memory step bit is named from memory step plus resistor. So sometimes resistive RAM means by using memory step. Getting the point? Okay. It's since it demonstrates the hysteresis property of the ferromagnetic core, memory and power dissipation nature of resistor. Okay. So in short duration, just a little bit discussion, but okay. Where we can use this memristor, so memristor application, you can use as a crossbar array or discrete. So crossbar like in analog or digital. In analog you can see neuromorphic networks. There also nowadays a lot of research going on. Field programmer will get array like FPGA. In FPGA kit also. Now it is FPGA kit. Industry working on this memristor based. Digital domain like non-volatile memory. I told memory. If you are using this memristor to design memory, that is a non-volatile nature. Okay. Then in discrete analog like see charge circuit, Smith trigger. I'm not talking all circuit because in short it is not possible to discuss this all. But in short, these are the places. I am basically why highlighted because I am focusing here. I am working on non-volatile memory is a memory. Getting. So basically it's the structures of the memory. You can see this is the top electrode, down that bottom electrode, two electrode is there. Just you can see it is anode, cathode. Getting not so this two layer is there, one doped layer, undoped layer. So titanium oxide materials inside is there, but when you apply the potential, so oxygen vacancy will increase or oxygen vacancy shift towards the other electrode. If oxygen vacancy increases, that means less resistance, it is increasing conductivity. So you can say in terms of resistance, when potential, then this doped region will increase. Means oxygen vacancy increases. When this doped region increases up to this, when W becomes D, that time less resistive path. And when W becomes 0, highly resistive, watch it. It will act like that. Okay? Okay, so memristor model, again this resistance theory. I am coming to the point. So basically first I designed this 2D theory. Just in short I discuss about the memristor, what is the fourth missing element, that the memristor it gives basically relation between flux and charge. So the rate of flux with respect to charge is nothing, it is the memristor. Okay, and basically in real life or started in the research basically after 2008. In 2008 basically in HP lab first time fabricated. Okay, before that up to theory people know, not more only those who are working. Okay, so see, first what I did, using this memristor I designed a memory, a very small circuit, but it is even if you are working on that, it is an emerging field. So definitely lot of parameters you cannot find. Even still researchers working on this, getting. Even I got also very few parameters, still struggling. Even so many bigger students working on this research, PhD scholar also I assigned, they are also working, getting. Still we are facing problem. But first time, sir, this is what I did. So this is the one memristor, this is the other memristor, and this memristor how it is connected. This is the positive anode cathode or like the positive negative. Okay, so this is one memristor, this is other. Here, those who are in my class, like when I taught yesterday. So you know this is the bit line bar. I think for you it is difficult. But this is a bit line that is connected with a column decoder. Okay, that is connected with sense amplifier. That is connected with a pre-charge circuit. Getting a point like 60. What is that? This is the data line. This is data line. We can write the data or read it. This is the word line bar that is connected with the row decoder. If you know the memory architecture, so external circuit left side, that is the right driver. Row decoder circuit down I thought that is the column decoder. In column decoder, right driver circuit, sense amplifier circuit, recharge circuit is there. Left side column decoder. So column decoder connected with this word line. So word line and word line bar that is connected. This is nothing. It is the bit line or bit bit cell. Bit cell means it can store one bit data only, either 0 or 1. Getting. So this is the storage node. This is the storage node. Okay. The storage node here we can store 0 or 1. Okay. So storing is one task, then accessing is the one task. Because memory main function to store the data and to retrieve the data. Okay. So storing you can store, but finally our goal is to retrieve, read and write. Otherwise the data is there. If I am unable to read and write, then useless. So retrieve is very. So this MOSFET is nothing, it is like switch. So when you are interested to write the data, the switch should be on. When you are ready to read the data, the switch should be on. Otherwise, only this put device we are using for storing. Get it? So how you can read and write data? See. So suppose, okay, I am reading the data. Suppose this is a 0. Here is code 0. What we have to do here and here, we have to apply. See, otherwise, as you is here you can store 1 or 0, no problem. If it is a 1, so that is same data. See, first write operation I am telling, then read operation. So write operation, what we have to do? See, write operation is initiated by turning WL and WLP on. How we can make this one on and this one on? Here apply rising pulse or high. WL is 1, WB is 1. No, sorry, 0. Because the stream of gate should be low, then it will be on. So 0 high, then it will be on. Getting? And even this is just like TV. So strong 1 and strong 0 can pass. Okay. So to write data is applied to data line. So whatever data you are going to write, suppose 0, then apply here 0. Suppose you are writing 1, then apply here 1. 1 means VDD, high. Okay. So to write the data applied to data line, and inverse of the data is applied to both BL and BLB. If you are applying here 1, then we are applied 0, 0. Getting a point? Okay. So here 0, 0, here 1, this is on. So here it will be on. So what will happen? So here 1, this is 0, this is 0. So 1 will be in forward bias. Forward bias means that resistance will increase or decrease. 1 will be in forward bias. So here 1, here 0. So here it will become less resistive path. So what will happen? This is less resistive means just it is like short circuit getting. So this BL start increasing, BL remains same. Okay. So if you want to see, it's so see BL remains same because starting at given 0 and BL increasing 1. Why? Because you have written at storage of 1 due to 1 resistors like the second side, the right side, its width increases, oxygen vacancy increases, so becomes less resistive, and that BL increases. So this is increasing. When this BL increases by, okay, so that is connected with so see here, yeah. So this BL is increasing, BL will same. In same way, read operation what you have to do. Prior to read operation, device BL and BL will discharge like 0, 0. Read operation is initiated by raising WL high, WL low. Okay. Once the transition of the transmission gate are on, BL and BL will charge. See, this is increasing, and this BL and BL is connected with a differential amplifier. I already talked. Okay. So this is the result. Whatever we got in Delhi, right? And this paper is published in one Scopus journal. Similarly, other device also you can use it like MTJ based. Only in short there is a layout. Okay.
Right now we are going for the handout, sir. Okay. So you see
software we have to install, otherwise I'll tell you, just you can download open source, okay, like micro:bit. You can design layout, okay. As Spice, if you are interested, then I'll tell you, there is a license synopsis tool that is very costly. But one way I can help you, you can download the crack version. I think one is working. Okay, in a real estate. So what you do, I'll give the link, you download that, then install, and how you can crack that key I give you, then you can start. Okay, before that what you do, that manuals or that, yeah, I'll share it if required based on that. Today just we see this layout part. So this is the micro:bit software. Okay, what you have to do, this is micro:bit software, you can download, otherwise I will share it also. Okay, so this is the, I have this micro:bit. Okay, open this system. So this is the my, just it look like pedestal. Okay, so here in a right side, here given different types of
Guys, sir, you have given the URL of free downloaded software.
Yeah, they can do, but they have to download. Otherwise, we have to share that software. Software required. Open software. Can you download? Try to download. Micro. Micro. I can download.
MICROWIN.
But sir, they will do that. It will take time. Just
Okay.
how we are doing just learn. It will be good. Okay. Yeah, this time not faster. Later on, you can call me, you can WhatsApp the whole. Anytime I'll help you. No problem. Okay. So see right side here annual given. So this is the annual. So this annual first you can draw. That is the annual. Because PMOS only you can design inside annual. Getting my point? So that annual design here PMOS rate how you can design. So P diffusions put here like this is the P diffusion. Okay, this is the P diffusion. Then cross pass, this is the polysilicon. So this is the polysilicon. So suppose on here, so this is the polysilicon. Okay, so that is nothing. It is the see this polysilicon width is nothing. It is the channel length. Getting it? You know the layout design rule. So this is the polysilicon width. So that is the channel length. And this width of the P diffusion, that is the width of the MOSFET. So drain this side or this side or this side, so there is a symmetric any side you can get it. Okay, one more PMOS I am this is the other PMOS I am putting here. Get it? Again similarly polysilicon. So this is other PMOS. Okay, we can give name itself like see here I shape symbol. If click here, here you can put a like a MP1, like MP1 or 2 as you see. So you can assign its name. So that is a MP2. Then here again you can name it like a MP1. Okay. So before going to design this layout, first you have to draw the CMOS schematic. If you know CMOS schematic, is here that chop? No. Okay.
If you want to talk,
Yeah, actually, but time is not there. So first draw the schematic. Based on the schematic, we design the layout. Getting it? So this is the PMOS. Now we are going to design like a NMOS. The NMOS always is the outside of anvil. So here, this is the NMOS. Again, other NMOS you can see. You get it? This P polysilicon should cross. So here you can edit or delete option also there. Get it? Suppose if you want to delete this one, you can delete. Get it? Okay. So this is the delete. Okay, then yeah, so this is polysilicon width we can increase, so what we have to do, select this here, you can pass this one, yeah, so this is your other NMOS. So see what I am telling you in short. So I am going to draw the layout of 60 SM. So this is your one PMOS, this is the PMOS, NMOS, this is the one PMOS, this is the PMOS, okay, this is the ground, this one is a common, that is the VDD, okay, here this is your output of first inverter, this one, output of first inverter, output of second. So this input of first inverter have to connect here, input of second inverter have to connect to the output here, that is called cross coupled inverter. So this is the axis MOSFET. I already taught in first. Okay, so this is the MOSFET. This is the BL. This one is the BLB. Okay, this MOSFET can control the axis which can control by WL. This is your BL. This is the BLB. its name you can write Mn1, this is the Mn2, this is the Mp1, Mp2, this is the Mn3, this is the Mn4. So how many MOSFET here? 6 MOSFET. That's why its name is 6P as RAM. Getting? So this is the first schematic. What you do? Just it's a drain source. So this is the source. This is the source. This is the drain. This is the drain. This is the drain. This is the source. This is the drain. This is the source. Getting? Here randomly you can take. This is the drain. This is the source. This one is the drain. Source, drain, like that. Okay. Okay. This is connected here. WL. So now how you can design based on this. So this it's a sizing also I taught. Those who train by 60 SRM class, I taught sizing also important. If you are taking proper sizing, technology not is fixed like 60 nanometer. Width we are changing because aspect ratio you have to select proper so that its switching will be proper. Otherwise, so generally what we are doing, it's a W is equal to like 60 nanometer, L also 60 nanometer. Its L is 16, L for all 16 nanometer, W only writing, W is equal to 2W. Here W is equal to 2W. Okay, this one is the same. L is equal to 16, W is equal to 16. Here this W is equal to 32, this W is equal to 32. This is 1.5 times, so it is a so 1.5 into 60. This one also 1.5 into 60. That is the W. L is 60. So based on that, bits also have to change. Okay. So see, two PMOS I designed like MP1, MP2. So see, based on that circuit connections, see, this is your PMOS MP2. This one. First I am talking this MP2. Its source is connected with VDD, drain is connected with the drain of NMOS. Okay, so this source you keep here. So source is nothing but VDD. So what you do? Here VDD you can give. So VDD means one metal contact. So in top you can see metal contact. So here we will keep here one. So its a name you can give VDD. Get it? So terminal name should be proper, then there will be no confusion. VDD. That is the okay, one VDD given. So that is the source. This is the drain terminal of PMOS. Okay. And see, this is drain. So drain is nothing. So what we do here, one metal layer. Okay. So here we write it's a L. What is that? This is a H. So this node name is a H. So here you can name it's a name like H. So this is H. H. Okay. Okay. So its a drain is connected with H. Okay. And this polysilicon, see, this polysilicon means gate is common. Gate is common with this Mn2 and Mp2. So that is the red color. That is a common. Okay. So this is your Mn. This is the Mn2. This is your Mn2. That is the Mn2. So see, Mn2 MOSFET. One side again see this Mn2. One side is the drain. This is source. So source is connected to ground. This is connected with H. So H, this one is H. This is the H terminal. This side we have to connect the ground. So here, this more side you can shift down. Oh, sorry. Here again ground terminal we have to give, so you can give metal contact here. So this is nothing but its name you can apply here ground. So here it will be the ground. G and D. Okay. So this is the ground. So this is one MP2, MP2, MN2 finished. Getting. Now see, same this side other, this side other MOSFET is there. So its name is MN4. So here its width should be more. So other PMOS will draw here. Getting. And it is 1.5 times width. So this is other MOSFET. So here again, this is I'm just crossing this polysilicon. Not exact measurement. Measurement should be proper. Otherwise, area will be more, error will be. So that one I am not taking right now. Just a rough how you can put the device and how you can. Okay. So this is the one MOSFET. So its name is the MP4. MN4. Sorry, MN4. Getting 4. So this MN4. See, one terminal is connected with H, other terminal is BLB. So, see, this one terminal is H. This side again we have to increase this layer. So this layer we have to increase. Okay. So here again one. What is this? Its name you can give like BLB. So here you can put a BLB. BLB. So that is your. So one part finished. This person's layout I have design not complete. Similarly, this part again you have to design. Now time is less. Same way you can do this left side. Otherwise, I am closing this one. Already my design is there. That one I am showing. Okay. I am closing this one. So we have 5 open. Okay. Then this is not my. So I have designed this 60. So this is the 60 same way. One side I got it. This is same way this side and all connections I have put. So according to the layout design rule, here should be 6 lambda space. If you are not putting this 6 lambda space, then error will come. Similarly, this space should be this width should be fixed. So in design micro lambda design rule or micron layout design rule that is mentioned very clearly between two layers spacing, width of the metal layer, width of the polysilicon, width of the P diffusion, width of the N diffusion. Each layer's width is a fixed. So you have to take accordingly. Okay, and spacing also should be, wide spacing should be proper. Without if you are taking closer, then maybe in circuit it will be short circuit or your circuit will be damaged. If you are taking too much more space, the error will not come, but area will be more. So area problem. So that's according to that rule we have to follow in design. How you can calculate itself. So design and checker facility there. So you can check see here error showing. So this space issue is there. So spacing between contact less than 4 lambda, we have to increase. Okay, then it will be low error. Okay, suppose low error, then how you can measure this? So for measuring area, so this is the measure distance. How we can measure C? Actually, this is the. So this is the actually. So this width, vertical width, this is horizontal. So this much area, it will take by one width cell. Okay. So this is the length, width, length into width. You can multiply 2.9 micrometer into, that is 1.0 micrometer. that much area taken by this one bit cell. If you are going to design like 64 into 64, that is a 512 byte. So you have to multiply this into how much? 4048. Because 64 into 64, that is 4048 bit. So 4048 bit into this much area will be the exact area of 512 byte memory. Okay. So this way you can design. Even you can design this layout in microbit. It is open source, but you can publish paper. No issue. Getting. Now it's short, but not I'm showing you that key have to. Okay, this is a microbit. Now other software. Showing this X slice. Okay, so this is the synopsis. X spice tools. Here I have written code just I am showing. So this is the 6-bit DRA. So here you can check it's a code. So same way, this is the code for this circuit. This circuit, how system will understand this is the circuit. So this terminal name and device name you have to write up to this is common as you can check. So 1027 means we are going to simulate at 27 degree some temperature. Global VDD means ground and VDD is global type. We have to define. Then dot param T step. So we have to define clock. So rise time, all speed, all duration. That one we have to define. Then this is the library. Other I like this one. Yeah. No. Code for measuring the parameters. So device library should be there. Like device library, device model. This model like 16 nanometer model. Someone like landscape for university. Someone design that like device device 16 nanometer technology. One MOSFET model is there. It's the land, weight, all parameter of MOSFET is defined in that. So that model we are using. That by using that model we design the circuit. Okay, that system will understand what is the land, what is the weight, what is the resonance, what is the threshold voltage, what is the every all parameters in that model mentioned. Just what we have to do in circuit, like this is the circuit code. This one we have to write here. Yeah. So this is the net list. This is the net list means how it is connected. Like see, MP1 its drain is connected at L. MP1 drain is connected at L. Its source is connected at VDD. Okay, body is also connected at VDD. It is a P type, so it is PMOS. Its width is W because in library W is mentioned it is 60 nanometer. L is L, that is its length is 60 nanometer. And above it's a lambda, all parameters about that is common for all. Only this we have to. I told this MP to same W is equal to W, L is equal to L. But this NMOS and this NMOS width will be twice. So see, it is N type, W is twice of W. Here also twice. It is 1.5 times. It is 1.5. Means if you are writing this netlist, means the system will understand width of this MOSFET is twice. Width of this MOSFET is 1.5 times. So this is nothing, just netlist of circuit design. Then this is nothing, it is the measuring command. So measuring command like that. So see, dot measure star we are using to actually this one star or actually So dot command we are using star remove. Then you can measure. So measure that is 16 not modify this actually. No, randomly other ones like doing research. Okay. Yeah. So this one. Sorry. Here commented. No need to this. See this one. Measure TRA. TRA means suffix. So we are going to measure read access time. So what we have to do? We have to trigger VWL. Why V? It is voltage type. So where we are applying at WL. So WL we are applying rising pulse. So when this voltage is above threshold voltage, this one and this one will be on. Get it? So for that we have to apply triggering. Its value should start from 0.00 to 0 with almost 0, and it will rise to first rise. What is our target? Target is BLB. BLB, what I told her, if it is BLB here 0, then this one will discharge. If here 0, then this one will discharge. So based on the stored data, either BL or BLB will be discharged. So suppose here 0, this is discharging. So our target is BLB. It is voltage type, and value when it is supply minus 0.05, because in H space we have not connected that sense amplifier. So sense amplifier differential type. Differential sense amplifier, when the difference between two input is 50 millivolt, then it will send. So that code I have written here, teacher, we are intelligent. So I have written here like value supply minus 0.050. So when this voltage will discharge by 50 millivolt, how much time taking? So that time is nothing to read. So if you simulate this, then graph or result will come. I am not going to do that graphic, that actually key required. Right now I cannot use it that time because it is unethical. Okay, so that one I am also just code I can explain. Okay, so what we have to do here, we have to click on simulation. Then you can check in this graph, but it is by default license error. Okay, so that one I can answer. Okay, next time or any help you can note down. Yes, yes. ये सब नोट कर सकते हैं. You can note. Yeah, this is yeah. So these are the my mail ID. Even if you are interested, sometimes you can call also no issue. 8709965022. Okay, but not always. Important one then. Okay. So these are the, even you can search in GIT main website, my details you can find, Google Scholar also, research gate also. Okay, just name search, everything you can find in. So, okay, thank you.
Thank you.
Actually, lot of things I cover in a whole day. That is not possible because it is a complete 2-3 years mark. So just in short time.
We might have more time.
Yeah, more
I
time.
should have 5 years. Sir.
Hello. So,
Harish.
good evening everyone.